This is your integrated 3 little mini lecture on section 10.1.3. Should I read this? I'll go ahead and read it. It says, so far you've developed strategies that compute the sum of an arithmetic series for a given number of terms. However, what if the number of terms is unknown? For example, in the lottery example from lesson 10.1.2, what if the time of the drawing has not yet been set? How can you write a general expression that will represent the total number of tickets sold after any number of hours? Well, I think I've been already kind of telling you guys that it's n over 2 times the first term plus the last term. And that's, if you were working in your teams together, you would be kind of discovering that on your own. Since you're not able to work in your teams right now, I'm kind of showing it to you. It says, as you work with your team today, pay attention to the different ways to represent a series. Many of the strategies introduced today may be helpful in the future when thinking about sums of other types of series. When your team discovers a new way to see the sum of a series, be prepared to share the idea with your classmates. So we were kind of hoping that you were able to see the sum of a series as those rectangles that we were drawing. You can stack the second half onto the first half and make a big rectangle, or you can do that thing where you pair them up and then add the pairs. So what I'm going to do is, I think I'm just going to go through this first question, and then the other questions are getting you ready for 10.1.4. But since I'm just going to show you how to do 10.1.4, I'm probably not going to really talk about the questions that are getting you ready for it. So we're just going to do 10-37. It says, consider this series. What's the sum of the first 3 terms? So the first 3 terms, well, we can tell. It's just 6, right? Because you just go 1 plus 2 plus 3. We can try this is our formula that we've found to work. We can try this and see if it works. Put the first term in here, that's 1. The last term, let's do it here. The first term is 1 and the last term is 3. Half of n, well, there's 1, 2, 3 things, so half of 3 is 1.5, and it works. What about the first 10 terms? Well, for the first 10 terms, we'd have to figure out what the 10th term is. So wouldn't the 10th term just be 10? Because it would go first, second, third. So it would just be, and there would be 10 things. First term would be 1. The 10th term would be 10. That'd be 55. Get the idea? So what else does it say? What's the sum of the first n terms on letter B? That is, what is 1 plus 2 plus 3 plus 4 plus blah, blah, blah plus n? If you don't know the last term and you don't have a way to figure it out, you can write it using n. So that's it. It's n over 2 times the sum of the first and last terms. Well, the first term was 1. The last term, remember that it went dot, 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 n. So the last term was n. So there it is. They're just wanting you to solidify this formula in your mind. I'm hoping that most of you have been using it and you get it already. But let's read letter C. It says, legend has it that long ago, when famous mathematician Carl Gauss was a young student, his teacher tried to keep his class busy by giving them the task of computing the sum of 1 plus 2 plus 3 plus 4 all the way up through 100. He stunned his teacher and his classmates by calculating the sum quickly without assistance. What is the sum of the first 100 counting numbers? Well, I gave you guys, some of you who got done early with something, I think I gave you a problem of the week. And it was something just like this. And some of you guys just stuck them all in your calculator and added them all up. And ta-da, here it is. I'm not sure how many of you actually found a formula for this. But now we know that since this is linear, it's going up by 1 every time, we know that we can just pair like the first and the last number makes 101. The second number and the second to the last number adds up to 101. The third number plus whatever number is before 99, it all adds up to 101. So there's a bunch of pairs of 101. How many pairs would there be? Well, if there's 100 numbers altogether, if you pair them up, there would be 50. So it'd be 50 times 101. I wrote it all out for you by putting it in my formula. So here's what I was saying. 100, 1 plus 100, that's 101. But 2 plus 99 also equals 101. And 3 plus 98 also equals 101. And if I kept pairing them together like that, I would have 50 pairs. 50 pairs of 101. So it's not always going to be that easy, because sometimes, like they were saying, maybe you don't know how many numbers are there, but how many numbers there are, and you have to use some ends and things. But this right here is pretty easy. We're just, we have a formula. This is the formula for the sum of an arithmetic sequence right here. Okay, we've already revealed this to you, and there's a math notes box about it. So that's pretty much what you were doing in 10.1.3. I'm not gonna do these problems, but I want to show you that it is possible to, sometimes we would have a reason to add one series to another series. And so that's what they're showing right here. They have a series that goes 1, 2, 3, 4, 5 all the way up to n. And then they have another series that's just 2, 4, 6, 8, 10. And then if I wanted to, if I had a good enough reason, I would be allowed to add these up, add the first terms. And if I added them up, I get a new series, and it's 3, 6, 9, 12, right? And keep going. And if I did want to find the sum of the series, well, there's the first term and there's the last term. And so I would just use my same formula. So I'm not going to really talk about that in this lecture, because that's going to come into play when we start looking at some other series. It turns out that there are other series besides arithmetic series. And to derive the formula for summing those up, we might have to do some little maneuvers like this. So we'll talk about that next time.